Welcome, everyone. So, if you're tuning into this explainer today, it's probably because you're finally ready to look way past the surface of what we just, throw away. Actually, scratch that. As an engineer, I really want to reframe how we look at waste management entirely. We aren't just throwing things away, because honestly, there is no magical away. What we're actually dealing with here is a massive, incredibly complex chemical engineering puzzle. Today, we're going to decode the literal molecular building blocks of our garbage. We'll look at the exact chemical traits that dictate how our waste behaves, how it breaks down, and just how much hidden energy is locked inside.
Okay, let's dive into this. Here's a quick look at our syllabus for this explainer. We'll start with an introduction to waste chemistry, then move into biodegradable organic components, tackle combustibles and synthetics, look at measuring energy potential, and finally wrap up with ultimate and proximate analysis methods.
All right, Section 1, an introduction to waste chemistry. So why do we even care about the chemistry of a landfill? Well, it's because the chemical makeup, stuff like the products of decomposition and heating values, literally dictates how waste behaves throughout the entire management system. To engineer a proper solution, we absolutely have to evaluate waste across three distinct chemical profiles. First up, the purely chemical traits. We're talking pH, nitrogen, phosphorus, potassium, or NPK levels, total carbon, the carbon to nitrogen ratio, and the calorific value. Then we have the biochemical characteristics. This covers carbohydrates, proteins, natural fibers, things like that. And finally, the toxic profile. This is absolutely crucial. Here we screen for heavy metals and pesticides, and we run what's called a toxicity characteristic leaching procedure, or TCLP. Honestly, knowing these three profiles is exactly how we figure out if a batch of waste should be burned as fuel or if it needs specialized material recovery.
Moving right along to Section 2, biodegradable organic components.
Now, let's zoom in on the specific molecular families hanging out in our organic waste. The first big one, carbohydrates. You'll find these mostly in food scraps and yard waste. We're talking sugars and polymers of sugars, like starch and cellulose, with the general formula CH2O taken X times. Now, here's the interesting part. These carbs readily biodegrade into carbon dioxide, water, and methane. But from a purely practical standpoint, decomposing carbs are like an all-you-can-eat buffet for flies and rats. Because of that, in a real-world management facility, you just cannot leave them exposed any longer than strictly necessary.
Next up on the list, we have proteins. These are complex compounds containing carbon, hydrogen, oxygen, and, this is the kicker, nitrogen. They consist of an organic acid with a substituted amine group, which we write as NH2. Now, proteins make up roughly 5 to 10% of the dry solids in your typical trash. When they completely break down, they form amino acids, which is fine. But the real-world consequence of partial decomposition, that produces amines. Look, if you've ever walked past a dumpster on a hot day and caught that intensely awful, putrid smell of rotting garbage, yep, hit the nail on the head. That is the unmistakable chemical signature of amines. Our third organic category is lipids, so fats, oils, and grease. And wow, just look at this number, 38,000 kilocalories per kilogram. That is an incredibly high calorific value. It makes waste with a lot of lipids an absolute goldmine for energy recovery processes. But there's a catch. They present a really frustrating physical challenge. Because they melt just slightly above ambient temperatures, they turn into a liquid during decomposition, which just adds to the messy leachate at the bottom of a landfill. Plus, because they don't dissolve well in water, their biodegradation rate is actually super slow. Okay, let's shift gears to Section 3, combustibles and synthetics. Let's pivot away from biological breakdown for a second and look at thermal treatment. When we're talking about burning waste for energy, we basically divide the world into two camps. On one side, we have our combustibles. This includes natural fibers like paper and wood, along with plastics. These have those high heating values we absolutely want for incineration. On the flip side, we've got the non-combustibles: glass, ceramics, metals, dust, and ashes. These inert materials generate basically zero heat, yet they make up 12 to 25% of dry solids, so they're literally just adding dead mass to our whole system. Let's dive a little deeper into natural fibers to see how they fuel combustion. Natural fibers are mostly made of cellulose, which is a massive polymer of glucose, and lignin, which is made up of benzene monomers. Now, both of these are pretty tough for nature to biodegrade, but man, are they highly combustible. Just look at the breakdown. Paper products are basically 100% cellulose, cotton is about 95%, and wood is roughly 40%. Because of this, oven-dried paper yields anywhere from 12,000 to 18,000 kilocalories per kilogram. Wood hits around 20,000. To put that into perspective for you, pure fuel oil sits at 44,200. So, high fiber content, that makes for some seriously excellent fuel.
Now, what about synthetic organic materials, plastics? First, draw your attention to the unit change here. This is 32,000 kilojoules per kilogram. Plastics pack a massive heating value, which technically makes them amazing for incineration. But here's the rub. They are incredibly resistant to biodegradation. They just sit there in a landfill forever. This paradox, great for burning but terrible for the earth, is exactly why recycling plastics is such a massive, urgent priority. We really need to keep them out of standard disposal sites.
And this brilliantly illustrates the danger of combusting certain synthetics. Let's walk step by step through the real-world chemical chain reaction when a specific plastic, like polyvinyl chloride or PVC, gets incinerated. When PVC is burnt in a combustion system, it doesn't just give off heat, it produces highly toxic dioxins and acid gas. Inside the power plant, this causes severe corrosion to the expensive machinery itself. And worse, if it gets released into the atmosphere without some heavy-duty scrubbing, it's directly responsible for creating acid rain. Definitely not what we want.
All right, Section 4, Measuring Energy Potential. So we've been talking a lot about heating values, but how exactly do engineers figure out the energy potential of all this junk? Well, the gold standard for measuring heating value is the Baum calorimeter test. In a super-controlled lab setting, a dry sample is burned, and the heat generated is measured at a constant 25 degrees Celsius. Now, because this is well below boiling, any water produced remains in a liquid state. But we have to account for real-world thermodynamics. Out in an actual furnace, combustion gases shoot way above 100 degrees Celsius. That means the water turns into vapor, and when it evaporates, it physically absorbs and steals away some of that precious heat energy.
Finally, Section 5. Ultimate and proximate analysis.
To truly optimize a waste-to-energy facility, just knowing the heating value isn't going to cut it. We have to bring in two final, highly rigorous analytical methods to map out our waste sample completely. The first one is called ultimate analysis. You can think of this as the elemental roll call of the trash. We're locking down the exact proportions of carbon, hydrogen, oxygen, nitrogen, and sulfur. Why? Because it is literally impossible to perform a mass balance calculation for a chemical process without those numbers. It also meticulously checks the ash fraction to flag potentially harmful environmental effects, specifically hunting down toxic heavy metals like cadmium, chromium, mercury, and lead, while also noting harmless ones like iron and magnesium. Here's what an ultimate analysis looks like for a typical municipal solid waste sample. Notice the stoichiometry going on here. Carbon and oxygen are the heavy hitters of the organic fractions, sitting at 25 to 30% and 15 to 30% by dry weight, respectively. Meanwhile, nitrogen and sulfur remain super low, usually well under 1.2%. But don't let those small numbers fool you. They are absolutely critical to monitor so we prevent noxious gas emissions. And the ash fraction, as you might expect, is kind of all over the place, varying from 12 to 30%. So, the crucial point is this. While ultimate analysis gives us the exact chemical elements, proximate analysis evaluates the pure physical combustion properties of our refuse-derived fuel. We break it down into 4 fractions. First, moisture content. This just adds dead weight, and boiling it off literally steals heat from the furnace. Second, ash, more dead weight that generates zero heat. Third, volatile matter. This is the highly combustible good stuff that flashes right into gas. And fourth, fixed carbon. This is the stuff that stays behind on the furnace grates as stubborn charcoal, which requires a much longer retention time to completely burn away. Visualizing this really helps bring the engineering reality into focus. In a typical municipal solid waste profile, a massive 53% flashes instantly into volatile matter gases. About 20% is just pesky moisture we have to boil off, and another 20% is inert glass, metal, and ash. Only about 7% stays behind as that fixed carbon we just mentioned. Understanding this exact ratio is like having the cheat codes. It dictates the airflow, the grate speed, and the optimal temperatures of a modern waste-to-energy plant. Which brings us to the end of our explainer today and leaves us with a really provocative question to ponder. If our solid waste is, as we've clearly just seen, merely a complex mixture of chemical energy and distinct elemental components just waiting to be unlocked, why in the world do we still treat it as a problem to be buried in a hole, rather than a resource to be carefully engineered? Understanding our waste at the molecular level isn't just some boring academic exercise. It's literally the very first step toward building a truly sustainable closed-loop future. Thank you so much for joining me for this explainer today. Keep analyzing, keep questioning, and I'll see you next time.